This video, we're going to talk about partial fractions. It's the last main method that we're going to learn to integrate something. So partial fractions helps us to differentiate rational functions. So a rational function is just a fraction where the numerator and the denominator are both polynomials. So this method helps us to decompose this rational function into something simpler that we can integrate directly. So let's see. We have some conditions. If we want to apply partial fraction method, we need to have, like I said, a polynomial over a polynomial. But the condition here is that the degree of the numerator must be less than the degree of the denominator. Okay, so what happens if the degree in the numerator is bigger than the denominator? Here we need to perform a long division. Once we perform a long division, we're going to get something of the form of like a plus r over x, r of x over q of x. So here a of x is just a polynomial that I can integrate directly, and then r over q here is a rational function that I'm going to apply my partial fraction method to, so I can integrate easily. So here, after you apply the long division, the degree of r is always less than the degree of q, so that's why I can apply the partial fraction method directly. Okay, so now let's look at this example. Here I have a polynomial divided by a polynomial, but the degree of the numerator is 2, which is bigger than the degree of the denominator, which is 1. So here we need to apply long division. So to apply the long division, you always put the numerator inside of your long division here and the denominator here. So how do we perform long division? Let me remind you. You take the first term with the highest degree and then divide it by the term with the highest degree here. So x squared divided by x, this is just x. Once you get your x, you're going to multiply. So x times x, x squared, x times -1, that's negative x. And then you're going to subtract. X squared minus x squared goes away. Then 4x minus x, that's just 5x minus 6. Now when do we stop? When we get something with degree, like the degree of this polynomial here is less than this, we stop. So here, since we have the same degree, we have to continue. So highest degree, 5x, highest degree is x, so 5x divided by x, that's plus 5. You multiply, you're going to get 5x minus 5, and then you subtract them. So this is 0, then -6, -5, so that's -6 plus 5, so that's just -1. Which means I can write my function as x plus 5 plus the remainder, -1 over x minus 1. So now after applying the long division, you can just put it back in. So now I have the integral x plus 5 plus -1 over x minus 1 dx. And this I can integrate easily. And that's it. So here we haven't started talking about partial fractions yet. Here we're just applying long division, so I can, like, just a reminder of how to do it. So let's start with the cases that we have for partial fractions. So partial fractions is all about factoring the denominator and then writing the whole expression as a sum of different fractions. So let's see how that works. So the first case is when we have linear factors for the denominators and we don't have anything repeated. So if q was my denominator and I can factor it as linear factors, and we don't have any factors repeated. They're all distinct. So what we do here, this is the method of partial fraction. You get the function that you started with, which is a rational function, and then you take each one of these factors, you make it a denominator, into different fractions, and you put constants in the numerator. So we're kind of like building different fractions where if you want to simplify, once you get like a common denominator, add everything up, you're going to go back here. So the reason why this is helpful is we're going to start with something that's difficult to integrate, and then we're going to decompose it into things that we can integrate easily. Okay, so how does it work? So once you decompose it into these fractions, you're going to have the constants a1, a2, up to an unknown. So the main goal is I want to find the values of these constants. Once you find them, you put them back in and you integrate directly. So let's see. If I have this example, I have my p of x is just x minus 4. Q of x is this quadratic polynomial. Now the first thing that you want to check, is the degree of the numerator bigger than the denominator? If that's the case, you apply long division. If not, you can just apply partial fractions directly. So here, since the degree of the numerator is less, I can apply partial fractions directly. Then, if your denominator is not factored, you need to factor it using factoring methods. And then, let's see what happens. Now I have two linear factors. We don't have any repeated factors, so we just apply the decomposition that we talked about here. So I just take a constant a1 divided by one of the factors plus a constant a2 divided by the other factor. So now the rational function that we started with is equal to these two fractions, so we decomposed it. So now we want to find the values a1 and a2. So let me show you how that works. Now since I have two fractions, so what's missing in the denominator here? Obviously x minus 2. So I multiply by x minus 2. Now, so in this example, I'll do like the long methods with all of the steps, but in the next examples, I'll just do it directly, and this is how you should do it. Unless you want to do all of the details, that's up to you. So now, a2 is missing x minus 3, and we're going to get this. So now, all of these fractions have the same denominator. So now, if I want to combine this, so now I have two fractions with the same denominator. This means that my numerators are equal. So I'm going to have x minus 4 is equal to a1 x minus 2 plus a2 x minus 3. And that's it. So now, if you distribute, similarly here, this is 2, okay. Now if I take common factors, I'm gonna get x, then plus, and all of these are constants. So now what happens, I want to build a system of equations and then solve these equations to get the value of a1 and a2. So here, the coefficient of x is 1. And the coefficient of x here is a1 plus a2. So since these two polynomials are equal, the coefficients of x and x squared and so on must be equal. So here the coefficient is 1, must be equal to a1 plus a2. And then the constant term should equal to the constant term. So I get this system of equations, which you can solve easily. So if we take the first equation and write a1 to be 1 minus a2, and then we plug it into the second equation, we should be able to solve it. So now I get negative 4 is equal to negative 2. Then instead of a1, I'm going to write 1 minus a2 plus minus 3a2. Now let's distribute and then solve it for a2. So negative 2 is going to be equal to negative a2. Then my a2 is just 2. And then from it, I'm going to have that a1 is just negative 1. So now the main thing that we have to do is done. I found the values of the constants. Technically, I'm almost there. So now the integral, since this is equal to this decomposition, I'm just going to plug in the values of a1 and a2 back in. And integrate. And now this is just ln of this is just ln of x minus 3 plus 2 ln of x minus 2 plus c. So here we started with something that's very difficult to integrate, we don't know anything about, into something that we were able to integrate easily with just one line. So that's why partial fractions are helpful. So partial fractions are used when we have rational functions. That's the main idea of partial fractions. Okay, now what happens if I have repeated linear function? What happens if I have x minus 2 squared? What do I do then? So technically it's the same exact idea, but instead of having a over that linear function by itself, I'm going to repeat it again. So I'm going to repeat it as many times as like how many times the So as many times as my factor is repeated, I'm going to repeat a fraction that's going to represent it. So for example, if I have x minus 1 cubed, I'm going to have to represent this factor into 3 fractions. So we're going to have a constant of x minus 1, then plus a2 over x minus 1 squared, and then again a3 over x minus 1 cubed, and so on. If I have x minus 1 to the 5th, I'm going to have 5 fractions, and so on. So let's try this example. Here I have 2x over x plus 1 over times x plus 2 squared. I have linear factors, but one of these linear factors is repeated twice. So this means I have to have 2 fractions for that factor. So let's see. Now x plus 1 is easy. I just take x plus 1 and then a2 over x plus 2. But since x plus 2 is repeated twice, I need to have another fraction that's going to represent it. And we square. Okay, now be careful. Here, I knew that I'm going to apply partial fractions directly because the degree of the numerator is less than the degree of the denominator. Okay, so let me show you the faster way of applying partial fractions. So here, instead of having a common denominator and equaling everything, then add them up, what you do is you take the numerator here, 2x. Now this is going to be equal the first constant, then anything that's missing from this denominator. So here this denominator is missing x plus 2 squared. Then plus a2. Now this denominator is missing an x plus 1 and an x plus 2 because I want to get the same denominator from like this. Then a3 is just missing x plus 1. Then what you do is, now we need to simplify. Just distribute the parentheses. Okay, now this part here doesn't have an x squared, so I'm going to have a 0 as the coefficient of x squared from this side. Now from this side here, I have an a1 with my x squared, so I'm going to have a1. Then I have an a2 with my x squared, so I'm going to have a plus a2. And I don't have any x squared here, so I don't have a3. Then if you look here, the coefficient of x is 2. Oh my god. Okay. 2, yeah. So if you look to the other side, I have 4x, so I'm going to have 4a1 plus I have 3x plus 3a2, and then I have it just an x here, so plus a3. And then for the constant term, it's 0 here, so this is 0. Then 4a1 plus 2a2 plus a3. And now we have a system of equations that we're going to solve. So now from the first equation, I can write a1 in terms of a2. So a1 is just negative a2. Now let's plug this into these two equations. So I'm going to get 2 is equal to negative 4a2 plus 3a2 plus a3. Then 0 is going to be equal to negative 4a2 plus 2a2 plus a3. If we simplify, two is equal, and then 0 is equal to negative 2a2 plus a3. Now if we subtract this from this, we're going to get negative 2 is equal to negative a2, then a2 is equal to 2. Just subtract the equations from each other. And then if you plug that back in to get the value of a1, a1 is just negative 2. And lastly for a3, just plug any of the values, either in this equation or the equation that we started with, but it's just easier to plug it here. So a3 is just 4. Okay, so now if we plug everything back into the fractions, we're going to get this integral to equal negative 2 over x plus 1 plus 2 over x plus 2 plus 4 over x plus 2 squared. And this I can integrate quite easily because these are just ln's, and then if you take this to the denominator, you're going to get these for the first two terms. And now for this, if you take it to the denominator, to the numerator, sorry, the integral is just negative 1 divided by negative 1. So we're going to have negative 4 over x plus 2 plus c. So that's it. So it's not difficult. It's just a long process that you have to be very careful, especially with all of these calculations. Just one mistake could ruin all of the values. So just double check every step that you do, and that way your answer would be guaranteed in the end. Okay, now the last thing that we're going to talk about is when we have irreducible quadratic factor. So if we have a quadratic factor for the q, for the denominator, what happens then? So if we have a quadratic factor, the fraction that's going to represent it would look like this. I'm going to have ax plus b in the numerator instead of just a constant a. And I'm going to divide by the factor itself. Now, if this factor repeats, I'm going to do the same exact thing like we did for linear factors. I'm just going to represent it with multiple fractions depending on how many times the factor repeats itself. Now, when I say irreducible, this means I can't factor it. So if you remember from the quadratic formula, we used to do b squared minus 4ac. If this is less than 0, this means that my polynomial does not factor anymore. So let's try this example. Once you factor the denominator here, we're going to get x minus 1, then x squared plus x plus 1. Now this does not factor, because if you take your b, this is 1 squared, which is 1, minus 4 times 1 times 1, which is negative 3, so it's less than 0. This means I can't factor it, at least in real numbers, because you can factor it in complex, but we're not interested in that here. So I'm going to stop with this factors. Now nothing is repeated, so I'm just going to use one fraction to represent each one. And since this last factor is a quadratic polynomial, I need to have this in the numerator. And now to apply partial fractions, I need to find the values of these unknown constants. So here I have a 1, so 1 is going to be equal to a1, then the missing terms that we don't have in the denominator here. So I'm going to have x minus 1 times x squared plus x plus 1, then a2 with x and x squared plus x plus 1, and then the last numerator with x times x minus 1. So let's simplify. Or actually, this is just x squared minus 1 because it's the factor. This is just x cubed minus 1, then plus a2. Then here, what I'm going to do is I'm going to multiply this with this, and then this with that, without distributing a lot. So here, this thing I can write it as, just for simplification, x squared minus x. Then I'm going to multiply the x with this, so I'm going to have x cubed minus x squared for my a3, then plus b times x squared minus x. And this is all equal to 1. So now let's build our system of equations. Since I have an x cubed here, I'm going to start with that. Here I don't have any x cubed, so the coefficient is just 0, and then I have a1 plus a2 plus a3, and we don't have any b's. Then similarly for x squared, I don't have it here, so it's going to be 0. Then no a1s, I have an a2, and I have a negative a3, and a positive b. Then for x, it's 0 here. Then no a1s, I have an a2, and a negative b. And lastly, I have a constant 1 that's going to be equal to negative a1. And that's it. So we got the first constant for free, kinda. a1 is just negative 1. Then let's plug it into the first equation and see if we can simplify anything. Actually, how about we do this first? Because here we can solve it easily. A2 is just equal to b. So let's plug in the values and see if we can simplify. So for the first part, I have 0 is equal to negative 1 plus b plus a3. And then for the second equation here, I'm going to have 0 is equal to b minus a3 plus b. So we got two equations with two unknowns, so we can easily solve them. Once you simplify it and do the calculations, b is going to be 1/3, then a3 is going to be 2/3. So here, a2 is also going to be 1/3, and we got all of the unknowns. Let's plug them back in. So now I have the integral of negative 1 over x plus 1/3 over x minus 1 plus 2/3 x plus 1/3 over x squared plus x plus 1 dx. So this is just negative ln of x plus 1/3 ln of x minus 1 plus, let me take 1/3 as a common factor here and see how we're going to integrate this. Now here, if you look at it, you'll think, oh, maybe that's partial fractions again, since I have a polynomial over a polynomial. But this denominator does not factor, so partial fractions are not going to be helpful here. But if you think here, the numerator is the derivative of the denominator. So if you apply a u substitution with u equal x squared plus x plus 1, your du is going to be 2x plus 1 dx, which is perfect because it's this part here that we got in the numerator. So once you do that, I'm going to have 1 over u du, which is just ln of u, and u is this. So I'm just going to plug it back in and we're done. So that's it. I know it's like a long process with a lot of calculations, so you just have to be careful. But it's not too difficult. It just have these three main ideas. So now let's do a final example without actually integrating. Just let's set up the partial fractions decomposition and you can integrate it if you want. So here, the first thing that I need to check, my numerator has a degree less than the denominator, so I can apply partial fractions directly. Let's see. I have linear factors and I have quadratic factors, which means I'm going to have constants in the numerators and polynomials too. Now let's see. I have these two factors repeated. So I'm going to have two fractions representing this and two fractions representing this part. So let's start. For the first linear factor, this is just a1 over x plus 2, and we're done. Now for the second linear factor, I need two fractions to represent it. Plus a3 x minus 3 squared. Now this quadratic factor, I need to have a linear numerator for, but since it's repeated, I need to put it twice. And we're done. So it's pretty complicated. I'm not gonna ask you to find the values of all of these constants because it's going to be a very long process and probably mistakes would happen along the way. So the main thing here is being able to set up the partial fraction decomposition. Okay, so that's it for this section. These are some suggested problems, and you can do these problems from Lumen homework number 3. If you have any questions, let me know.